Hey everyone, thanks for attending today's webinar. So if you don't know already, Carbin is an app that's been developed with CSHub Research, and it essentially uses a smartphone to measure pavement quality and excess fuel consumption from within a moving vehicle. And so it's going to be the topic of our webinar today. And the app has been in development over the past 6 months. It's available on Google Play and the Apple Store. And basically, the work has been spearheaded in part by Jake Roxon, who's a PhD candidate at CSHub, and they've been working really hard on it over the past 6 months. So in today's presentation, he's going to be giving everyone an update on what he and his team have been doing and also what is next for the app. So if you have any questions about the presentation during it, there is going to be a little Q&A box in the lower right corner, and you can feel free to type whatever questions you have. We'll get to them at the end of the presentation. So without further ado, thank you, Jake, for presenting, and take it away.
Thank you. Hello, everyone. Today's webinar is a continuation of work that we presented in February at the beginning of this year. What started off as a Fix My Road project has now become a scalable platform for collecting data, which we can use to monitor performance of our roads, while also reducing CO2 emissions from driving. I'm Jacob Roxon, a research assistant at the Concrete Sustainability Hub, and today I will tell you how a smartphone application called Carbin enables the process for data collection and how the big data analytics allow us to unravel information that other apps and leading road quality measuring devices have not been able to do. That is, to access information that is critical for a sustainable and safer future of our road users. Before we begin, I would like to mention that this project is an outcome of collaborative effort of multiple faculty members, researchers, and students from MIT, Birzeit University, American University of Beirut, University of Washington, and University of Massachusetts, Dartmouth. This week, we have millions of people, kids, students, adults, people of all generations, but especially the younger ones, all over the world, trying to have their voices heard, to have our leaders do something about the climate changing, our planet warming up. The clock is ticking. The time is now. Take it to the streets. You may have heard on the news, in the media. The strike is happening, taken directly from the Global Strike website. This week will be historic. In over 150 countries, people are stepping up to support young climate strikers and demand an end to the age of fossil fuels. The climate crisis won't wait, so neither will we. Young people have woken up much of the world with their powerful Fridays for Future, school strikes for the climate. Now millions of adults are joining in a huge wave of that will kickstart renewed action all over the world. The urgency of the climate crisis requires a new approach and a just response centered on human rights, equity, and justice. Follow the actions and join the movement. Why? Because the climate is changing. Earth's temperature goes up and down from year to year, but over the past century, it has gone up quite a lot. The world is getting warmer, whether we like it or not. Imagine the hottest day you've ever experienced. Now imagine it's 6 or 10 degrees hotter. That's the type of future in store for us if we don't significantly cut our greenhouse gas emissions now. Carbon dioxide warms up the planet, and globally we have increased its amount in air by nearly half, mostly since 1960s. Even if this isn't convincing enough, scientists have been warning us for decades that humans are causing severe and potentially irreversible changes to the climate, essentially baking our planet and ourselves with carbon dioxide. Now, more than 9 out of 10 climate scientists agree that our carbon emissions are the main cause of global warming. Weather has become unstable. Ice is melting fast. Seas could rise by as much as 3 feet by 2100. But even now the changes are noticeable. The number of climate-related disasters worldwide has more than tripled since 1980s. This has an unprecedented impact on our economy, communities, and our lives. But now that many of us are listening, what do? We sure can do something about climate change, as we do have the right set of tools to make a change. But how do we adapt? We should, of course, focus on all sectors of our economy, but the sector that we're going to discuss here today is transportation. Why? Globally, transportation accounts for more than 1/4 of total emissions, which translates to more than 8 gigatons of CO2, a staggering 71% increase over 1990s values. The highest absolute increase was in road transport, which increased to 74% of total transportation emissions. But those numbers are probably quite difficult to make sense of. So let me explain this in terms of carbon sequestration and the number of trees needed to offset CO2 emissions the transportation sector creates. It would take about 9.5 billion trees to offset 8 gigatons of CO2, and those trees would cover an immense 25% of Earth's land. Could we replace every internal combustion vehicle on Earth with its renewable and green alternative? We should most certainly strive to do so, but the reality is that this won't occur anytime soon. So what else should we do? What else can we do? We should focus on our infrastructure. Pavement vehicle interactions contribute to more than 70% of pavement's life cycle, and its roughness, structure, and material translates to as much as 5% of vehicles' fuel consumption on highways and as much as 15% in cities when compared to a well-maintained road. Although it may seem this as a promising opportunity, this poses yet another challenge, which is how to establish a system for monitoring performance of roads for the global system of more than 50 million miles of roads, stuffed with more than 1 billion vehicles. You can see the current methods, although are capable of quantifying the state of our infrastructure under realistic set of conditions, which include traffic, weather, and budget constraints, fail to be efficient and effective at a larger scale. The laser-equipped vehicles cost in excess of $100 per lane mile of measurements, while the crowdsourced apps are designed to a very specific set of technical users, which contradicts the sole idea of crowdsourcing. But above all, both methods are designed to measure just the current state of our infrastructure without the ability to predict its future under the specific set of climate and traffic load conditions, not to mention vehicle carbon emissions associated with using the road. That's why we're here today. In this presentation, I will walk you through the theory of pavement roughness and fuel consumption associated with it, how Carbin offers an alternative and scalable solution to current approaches, and finally, I'm going to show you an example of impact of this work, followed by plans for future developments. A common measure to quantify ride quality, and hence the quality of the pavement, is called International Roughness Index. It was introduced by the World Bank in the 1980s and was quickly adopted worldwide. This IRI is simply an average suspension movement of the reference car, also known as the golden car, over the distance length. The unit is either in meters per kilometer or inches per mile, and here you can see some reference values. Since 1998, this figure has changed, where new pavements have now IRI values below 1 meter per kilometer, with as low as 0.5. But these measurements are generally done only for highway systems at yearly intervals, mainly due to high costs. How does the roughness look like? Well, if you were to measure a certain profile of the segment, you can actually decompose signal in the driving direction into different wavelengths. These wavelengths can be used to present a signal in terms of spatial frequency. For the road roughness, typical wavelengths are between 35 centimeters and 90 meters. Lower wavelengths are attributed to texture of tires, which adds additional fuel consumption. If you have experience driving with different types of or brands of tires, you may have experienced this firsthand. But going back to road measurements, what we are interested in finding here is how the spatial frequency affects vehicles' fuel consumption. To infer information about IRI, we use transformation as a function of spatial frequencies called power spectral density, which scales negatively with a factor called waviness number. Now, when we multiply this power spectral density response by a known reference value for a golden car, and we integrate it in a spatial domain, we can actually derive IRI values from spatial frequencies. How does this IRI affect fuel consumption? Well, each time your suspension system moves up and down, it scales with the speed to the second power multiplied by a damping coefficient. This leads to the loss of useful energy, which is supposed to move the vehicle in the driving direction. The idea is quite simple. The more we experience up and down movement in the suspension system, the higher excess fuel consumption is going to be. And for lower speeds, this effect has more pronounced impact. The best part is that since we're able to quantify the amount of excess fuel, we can identify the amount of excess fuel emissions for gasoline, diesel, or even electric vehicles which use electricity from non-renewable resources. We can determine these values analytically with known roughness and vehicle properties, where the vehicle is no longer the golden car, but rather the vehicle that you're driving. The key inputs into this integral equation are measured roughness properties and suspension properties of your vehicle. Now, how does this relate to smartphone measurements? Well, all smartphones now have accelerometers built in, which can measure in vertical direction the signal that we need in order to derive power spectral density needed to derive IRI, but only if we know suspension properties of your vehicle. So how can we do this with just a smartphone? All we need is acceleration of the body mass in the vertical direction, which actually requires X, Y, and Z accelerations, due to the fact that phone may not always have the same position in the vehicle. We also need GPS coordinates in order to be able to track the measurements and visualize them. As an output, we get vehicle properties, IRI, excess fuel consumption with carbon footprint, and some other useful outputs that you're going to hear about later in this presentation. Now, if we dive into the literature about different approaches, you'll see that there are three approaches for quantifying IRI. There's ad hoc engineering, where you obtain acceleration, you integrate it twice, and obtain some displacement, which eventually you can relate to roughness. Of course, when you do that, you assume that you're driving on a rigid, in a rigid vehicle, which imposes a significant error into measurements. But this approach might be suitable for identifying potholes. The second approach uses correlations. But the problem with correlations is that they're not transferable unless you have some kind of artificial intelligence system which learns the system response and is able to adapt to a new set of conditions. This requires calibration for any new type of measuring device. Lastly, there's a random vibration theory that uses a low-pass filter to derive power spectral density from smartphones measurements. However, this approach is speed-dependent and considers golden car properties. Now, despite some inaccuracies, none of these approaches is able to identify vehicle properties, nor can quantify the environmental impact associated with the usage of the road. That's where Carbin comes in. In the second part of this presentation, I will explain to you how Carbin approach is different and why, when compared to other well-established methods, it has more potential to scale globally. Before we can talk about how we utilize previously explained equations, I want to first give you an overview of the entire data collection and analysis process. It's quite an easy one with three main parts. First, we must collect data with a smartphone. The cell phone must be mounted in a stable position, but more on that later. Two inputs are provided with a cell phone: accelerations at frequency of 100 Hz, and GPS coordinates at the frequency of 1 Hz. These values are transmitted to the server on about 3-minute intervals. On average, we have seen that around 12 megabytes of data are transmitted for 1 hour of usage, which is dependent on traffic conditions. The app currently offers Wi-Fi compatibility, which means that if you record without internet access, you'll still be able to send it later. Once the data reaches the server, analysis begins, and assuming no interruptions in the data transfer, results are usually available within a few minutes of completing the trip. To begin recordings, mount the phone in a stable position and click record, which with internet access can be used in the background while using other apps. Or you can use Carbin as a GPS navigation. The GPS offers similar functionality for driving as Google or Apple Maps, but depending on the time of the day may not always offer the best traffic predictions. However, with more users, the accuracy of real-time traffic predictions is going to significantly improve. When you start driving, this is the type of acceleration signal that we need for analysis. As you can see, due to high frequency and noise, the raw signal doesn't mean much. However, as soon as you begin the power spectral density analysis for the right spatial wavelengths, you'll see that you can extract real-time road conditions. Then, using fluctuation dissipation theorem, we can quantify excess fuel consumption, as you can see in the bottom right corner figure. While we don't know vehicle properties, we know the range of values different suspension components can take. And using our model, we find that with enough data, modeled values converge to values that characterize the vehicle. Changing figures that you saw visualize data analysis that occurs on the server, but are not available to the user. However, once the analysis is over, the user is able to view the results. This is done so in the history section of the app, where the user can view all the recorded trips, which are categorized in the order from most recent to oldest. When clicked on the image of the trip, the user is able to access average trip results, which show distance, time, average IRI, and CO2 saving when compared to driving on a well-maintained road, which was derived using top 5% roads from our global measurements. Carbin result indicates the yield of results, which is indicative of the stability of the phone. Generally, 85% or higher results are obtained for a stable phone position. In order to learn more about the results, you can click on Info button in the top right corner. Lastly, in the settings section, the user can select different units for displaying data. The unique app ID is app-specific and can be used to retrieve data stored on the server. However, this number is randomly assigned for each downloaded app, so it is worth noting that if the app is ever deleted and reinstalled, the user will get a different app ID number. Now, throughout the presentation, I have mentioned several times that the phone needs to be in a stable position, but it doesn't really matter where the phone is, as the results here show. You can see that from a statistical standpoint of view, IRI signal follows the same pattern whether the recording comes from a windshield, phone mount, or the floor. We have conducted similar experiments for other phone positions to verify this hypothesis, and the outcome is always the same. So where exactly could you have the phone mounted? Any type of phone holder works well. You can also put your phone in a cup holder or on the floor. However, you should avoid putting the phone on your seat, holding the phone in your hand, or leaving it in your pocket. Of course, if there's a need, you can always pick up the phone. All that would happen at this point is the signal wouldn't be analyzed, but the analysis would go back to normal soon after the phone would be put back in a stable position. We have mentioned IRI, excess fuel consumption, and emissions. But is there anything else that Carbin can offer? First, additional advantage of using Carbin is information on vehicle properties. Here, for an example of GMC Acadia with 25,000 miles, you can see different suspension properties from frequency and stiffness values to mass and damping ratios. For comparison, you can see golden car properties used for deriving IRI values. To understand the impact of vehicle analysis, we monitored different types of vehicles for about 2,500 kilometers of analyzed data. In our sample, we had a total of 22 vehicles with both passenger and heavy-duty trucks. Interestingly enough, there's a strong link between two random variables: pavement road conditions measured as IRI and excess fuel consumption due to the suspension system. It is in the form of difference between covariance and extra fuel and IRI and variance of IRI that we are able to derive a signature response of the vehicle's suspension to road conditions. Here, despite significantly better road conditions for Audi A3, this car experiences higher excess fuel consumption when compared to a newer GMC Acadia. This can be clearly seen on this histogram, which shows the response of fuel consumption to road conditions for two vehicles side by side, with GMC showing lower excess fuel consumption. However, when measured for a longer period of time, GMC shows higher degradation rate of its suspension system when compared to Audi. This can be explained by the fact that GMC has been driving on significantly worse city roads, while Audi was driving mainly on highways. Similar type of behavior is derived from data collected by heavy-duty trucks. Since these vehicles have been maintained to roughly the same standard, we can see that their signature response is more or less similar. However, if we now compare two trucks of different age with different mileage, we can see that despite two trucks being of the same make and model, we can identify different suspension responses. This type of signature response is critical to deriving a heartbeat of the vehicle. The heartbeat can be used to monitor performance and predict deterioration, damage, or failure of mechanical components of the suspension, which generally do not have any electronic sensors that would tell the driver that there is something wrong. In the right corner, you can see the suspension system. You can see that the suspension system is composed of more than just shocks and tires. Rather, it is a complex system of many components where every one of them impacts handling, comfort, and safety of the vehicle. Using example of Ford Focus, you can see that different types of repairs can be associated with improving vehicle's heartbeat, eventually leading its heart rate back to normal. Anytime the heartbeat shows an elevated signal for an extended period of time, we know that something out of the norm is happening. The third benefit of using Carbin is ability to predict vehicle type and eventually also vehicle makes, models, and traffic density. Here you can see that using road and vehicle properties, we are able to create a model that with more than 80% accuracy is able to identify vehicle classes. Why is this important? For more accurate monitoring of roads and predicting their future performance with accurate traffic densities and loads. As a point of reference, states and cities currently only distinguish between passenger vehicles and trucks. The fourth benefit of using Carbin is ability to export data in an easy-to-understand CSV format, which can be viewed directly in Excel. Moreover, the user can now mark trips as either personal or business, which may be useful for the user to later identify trips, for instance, for tax purposes. All you have to do is click on the export button, and an email with a CSV file with all your trips is generated right on your phone. Now, number 5, a very interesting aspect of what we could do once we have enough data is eco-routing with $ or CO2 values assigned to each trip. As you can see on the left, Google Maps typically offers 3 different trips for driving navigation. Here we show an example for a short trip of about 6 miles between Watertown, Massachusetts and MIT in Cambridge. Phone GPS apps show trips by time, but they never quantify the cost of the trip in terms of fuel, emissions, or potential damage to the vehicle. Using an average of 2 return trips for each of the 3 routes recommended by Google Maps, we found that for better road conditions, the car is more fuel efficient with higher MPG values, which transfer directly to lower cost and CO2 emissions per mile, which for these trips show the difference of as much as 10%, as you can see in the bottom right corner in the table. Similarly, for a longer 20-mile trips between Lexington, Massachusetts and MIT. But this time, the difference in cost per mile can save the driver as much as 14%. Here, once again, we show that the higher quality of roads leads to lower fuel consumption. In conclusion, we can say that lower IRI leads not only to lower fuel consumption for the same traffic conditions, but also more comfortable rides and significantly lower damage to the suspension. Now, last but not least, the 6th benefit of using Carbin, the global impact and the Fix My Road project, with already more than 130,000 miles of analyzed data from 25 countries, with a total of more than 9 million data points. This leads to the next section of this presentation, impact of crowdsourcing. Here we show the global distribution of IRI values, which follow a bimodal pattern. This can be easily explained by the variation of quality between highway and city roads, which are maintained to a much lower standard, with an average value of roughly 2.1 meter per kilometer. On the other hand, highway roads show an average IRI value of around 1.3 meters per kilometer. The color coding that you see here uses Federal Highway Administration limits for IRI. Now let's link this information to fuel consumption and greenhouse gas emissions. When combined with average annual traffic density values, we can quantify emissions associated with the usage of roads. When compared to top 5% of roads, we see that red roads contribute to more than 130 tons of CO2 per kilometer per year. This would require more than 6,000 trees to offset these emissions. How is this helpful to states and cities? Let's take a look at the example of the city of Cambridge in Massachusetts. First and foremost, it is important to mention that in order to derive accurate IRI values, we need multiple measurements for each road segment. How many? In general, 3 to 5 measurements, but in order to monitor performance, we need continuous measurements from month to month. We have that for the city of Cambridge, which we use as an example for our case study. How to minimize road quality while how to maximize road quality while minimizing CO2 driving emissions with a fixed budget. As inputs, we need IRI, traffic density for different vehicle classes, street segments, and the number of lanes, which soon are going to be information that we will be able to obtain from Carbin's growing database. But for this case, we used some information from the City of Cambridge database. We assumed asphalt overlay composite for the pavement and used established regression models for its thickness thickness and age. We assumed non-changing climate. And all these information were used to create a pavement deterioration model. For the budget, we use reference budget as the critical budget needed to maintain the same network standard for the analysis period. Analysis period is selected to be 20 years, and the current treatment practice to be preservation. As a second budget, we choose a value 2 times higher than the critical budget. For the analysis, we consider different types of treatment actions using different common standard designs. For the reference budget, we find that incorporating long-term pavement treatment actions at the network scale can significantly improve performance of the network, here measured in terms of traffic-weighted IRI. We can see that for a current network of 2.3 meters per kilometer, switching from preservation to preservation and overlay during the period of 20 years can improve network's performance to an average traffic-weighted IRI of 1.65, which is a significant improvement for the same budget. Now, if we consider a budget that is 2 times higher than the critical budget, we find that for the optimal treatment plan, we can improve the network performance to reach good quality network for the specific traffic conditions. As you can see here, with the values reaching below 1.5.
For better roads, we find lower emission levels, and it is through the sustainable asset management that we can identify highest greenhouse gas reduction goals. For the city of Cambridge, we find that preservation and overlay approach is most economically and ecologically viable approach, with the cumulative carbon savings of more than 10,000 tons for the critical budget, and almost 20,000 tons of CO2 for the budget that is 2 times higher. We arrive at the conclusion that preservation and overlay treatment strategy performs best for the city of Cambridge. This is because, when compared to preservation only, segments will have smaller IRIs after overlay actions. Overlay actions also have longer-term benefits. For all cases, we also find that incorporating both materials performs best. This is because asphalt is cheap and has a high deterioration rate. Concrete is expensive and has a smaller deterioration rate. Now, for the conclusion section, Carbin is more than just a road quality measuring app. It provides real-time analysis with results available after the trip, ability to export trip files, monitoring road performance with comprehensive online database and mapping tools for different road classes, monitoring performance of vehicle suspension, and predicting failure. Essentially, Carbin is a heartbeat monitor for the road and the vehicle. In the future, in terms of the app development, we're going to implement improved GPS searching that incorporates work, home, and favorite places. There's going to be a fidelity program that is going to allow you to collect miles and get rewards. You're going to see push notifications on daily and weekly updates. And eventually we're going to create a system that is going to automatically record all the data in the background without the need of pressing start. Just you're going to mount the phone and the data is going to collect as you start driving. On the analysis side, we're going to be able to predict vehicles, makes, and models. Temperature of roads with deflection modeling, and monitor roads with identification of different pavement types versus concrete. In addition, we're going to incorporate behavioral analysis of drivers for accurate fuel consumption and accident risk maps. Thank you for your time. That would be everything for today. I'm sorry for the technical difficulties I had some issues with my phone, but I very much hope that you learned something useful today, and that I was able to convince you of the value that comes out of collecting driving data, and that is to convince you to join our Fix My Road project. The app is available for both Android and iOS devices and does not collect any information that could be linked back to the user. We have multiple social media accounts to share any news, which I would encourage you to follow to get access to the latest updates. Before I take any questions, I would like to make the final remark. That is, if you haven't done so already, please download the app and help us get to 1 million miles before the end of this year. Share the app with your friends, family, co-workers. And as always, if you have any suggestions for changes, any feedback, please share it with us. Once again, thank you for your time.
All right, Jake, thank you very much. So we have some questions here. I'm just going to go in the order that they were asked. So we have a question from Bob here. And Bob, if you want to unmute yourself, that way you can speak. We have everyone muted by default. Bob asked that my app only shows record without the navigation panel. And then he followed up by saying, I don't understand how the Wi-Fi application works. I can use Carbin without a phone signal. Can I use Carbin without a phone signal and download the info later? So can you maybe answer the first part, Jake? It's just about where the, he's asking about the record without navigation panel. He's wondering if there's a way to see an alternative to that.
So one thing is to double check that you have the latest version of Carbin installed. That's the first thing. Now, if you do, if in the App Store doesn't say that you can update the app, that means you have the most up-to-date version. In order to see the navigation, what you have to do is in the search field, you have to search for an address the way you would typically do with a navigation. And then once you click maybe I could go back to let me see if I can go back to this slide. And then there you go, this slide. So then you see when you search for places, when you search for a place of your interest, then the app is going to go into the navigation mode, and you're going to see 2, 3, or 1 different, or just one route depending on traffic conditions. And then you can select between different routes. All you have to do is click drive, and then the app goes into the navigation mode that most likely you're familiar with when you use Google Maps or Apple Maps. So then in the navigation mode, the app gives you guidance while recording data in the background. And then the other question was about the Wi-Fi, how it works with the Wi-Fi. So essentially right now, we don't have an immediate switch button to record only when there's, to send the data when there is Wi-Fi connection. But what happens is, to keep it simple, essentially, if you lose the signal, the app is going to store the data on your phone, and then once you have the signal back, it's going to send it to the database. Now, if you in an area, let's say if you're abroad and you don't want to share any you don't want to incur high costs for using the app abroad, all you would have to do is in the settings section prevent the app of having any data access while having the normal connection. So what that would happen is the GPS is still going to work. The GPS is still going to record your location, but now only when you connect to a Wi-Fi router, the app is going to send the data that you've collected. We're still working on making sure that the Wi-Fi compatibility works without any problems. Right now, we've kind of, it works, but I would say it's best if you do have internet access, the app performs best if you have uninterrupted internet access. Having said that, we do have the ability to essentially send the data when you lose a phone connection and then remove it from your phone storage afterwards. I hope this answers the question, but if it doesn't, please let me know.
There's one question that says, given the low GPS accuracy, how do you know which lane the car is driving on?
Giving the low GPS accuracy?
Yeah, how do you know which lane the car is driving on?
So the GPS accuracy is actually fairly good. The accuracy is sort of, it's more dependent on the sensor of your phone. So if you have an older smartphone device, the accuracy may not be that, the recordings may not be that reliable. But if you have a newer device, then sort of the accuracy of the GPS is up to the near, up to 1 meter. So it is possible to kind of figure out which lane you're driving in. Considering that the lane is typically about 3 meters wide.
And then Keith asks, any plans to have a voice turn by turn during driving?
I'm sorry, I didn't quite understand. To avoid what?
Are there any plans to have a voice turn by turn during driving?
System. Oh yes,
yeah.
Yes, the voice system. Yes, it is part of the navigation system. You just have to make sure that you have enabled voice. So if you go into the navigation mode, it does have voice commands.
And then Bob has another question. He's asking, he can't access too much info in the settings. Could you maybe expand on the settings part of the app?
If you tell us, if you make a suggestion what types of information you would like to see, absolutely. This is essentially what we, based on the feedback that we've received, that we thought would be useful for users. But if you have any recommendations in terms of what you would like to see, absolutely share it with us, and we'll try our best to incorporate it.
And then there's one final question here, and it's from Joseph. He's asking, are overlays feasible in an urban environment such as Cambridge due to matching curb and gutter elevations and maintaining bridge, underpass clearances, et cetera?
If they're feasible, that is something that we have not yet looked into. We're hoping very much that this information is going to be used by the Public Works, Cambridge Public Works departments, to see how they could incorporate it. But in general, I would say that yes, in theory it should work. They should work. Why they're not doing it right now, that's a whole different question.
All right, great. That looks like all the questions we have. So thanks again, everyone, for attending. And we're sorry for the technical difficulties here. That was unfortunate. But recording of the webinar will be posted shortly online, and you can review it, share with others. And additionally, we'll be sending out slides to the attendees. So again, thank you very much, and have a good day.